Good morning, everyone, and welcome. I am delighted to have you here today. My name is Dr. S.K. Singh, and I hold a PhD in this field. Today, we will be exploring the topic of robustness criteria in analytical method validation. Over the course of this presentation, we'll discuss what robustness means, why it's important, and how to establish it effectively in analytical methods. Let's get started and dive into this essential aspect of method validation. Welcome to our discussion on Introduction to Method Validation. In analytical method validation, our goal is to ensure that the methods we use are reliable and produce trustworthy results. Key aspects we focus on include accuracy, which tells us how close our measurements are to the true value. Precision is about consistency. If we repeat the analysis, we should get similar results each time. Specificity helps us confirm that our method can accurately measure the target analyte without interference from other substances. Linearity is important because it shows that our method can produce results that are directly proportional to the concentration over a certain range. Sensitivity refers to the method's ability to detect even small amounts of the analyte, which is critical in many pharmaceutical analyses. Robustness indicates how well our method can perform under small variations in experimental conditions, ensuring reliability in routine use. The United States Pharmacopoeia, or USB, specifically through 1225, sets out the requirements we need to meet for validating analytical procedures used in pharmaceutical analysis. This helps ensure that our methods are not only scientifically sound, but also compliant with regulatory standards, which is essential for quality assurance in the industry. Now, let's take a closer look at what we mean by robustness, or USB. Essentially, the robustness of an analytical procedure is a way to measure how well it maintains its performance when small, deliberate changes are made to the method parameters. It's about understanding how reliable the method is during normal use. To put it simply, robustness is all about the method's ability to tolerate small changes without losing accuracy or consistency. This is a crucial concept because in real-world testing, slight variations are inevitable. By ensuring a method is robust, we can be confident that our results are dependable, even if some minor adjustments occur along the way. This ties directly into our overall goal of developing reliable, consistent analytical procedures. In this slide, I want to highlight the typical parameters that are often varied during robustness testing of HPLC methods. When we talk about variations, we're referring to small, deliberate changes to see how they impact the method's performance. For example, flow rate is usually varied by about plus or minus 10%. This helps us understand how sensitive our method is to slight fluctuations in flow conditions. Similarly, mobile phase composition can be adjusted by about 2%, which might reflect slight variations in solvent mixing. We also look at column temperature, which can be varied by around 5 degrees Celsius, since temperature fluctuations are common in routine laboratory settings. Detection wavelength is another parameter, often adjusted by about 2 nanometers, to check the robustness of our detection system. Lastly, the pH of the buffer is varied by roughly 0.2 units to see how fluctuations might affect analyte separation and detection. Moving on, the purpose of conducting a robustness study is crucial. It's primarily about ensuring our method remains reliable under routine conditions. We want to confirm that the analytical performance stays stable despite minor changes. This helps us identify which parameters are critical and need tighter control. Ultimately, it reduces the risk of failure during quality control analysis, ensuring consistent, accurate results every time. This robustness aspect ties directly into the overall goal of developing dependable, validated analytical methods. Let's take a closer look at flow rate variation, which is a great example of how small changes can impact our system. Here, the nominal flow rate is set at 1 ml per minute, which is our target or standard operating condition. However, in real-world scenarios, slight deviations can occur, so we've tested at 0.9 ml per minute, exactly at the nominal rate, and also at 1.1 ml per minute, just above it. This helps us understand how sensitive the system is to these minor fluctuations. If performance remains consistent across these variations, it indicates good stability and robustness. By examining these differences, we can better predict how the system will behave under different conditions, ensuring reliability and accuracy in our results. Overall, understanding flow rate variation is crucial because it helps us optimize and control the process, maintaining quality and consistency throughout. Let's take a closer look at precision calculation under variation. This slide highlights how we can evaluate the accuracy of our measurements or models when there are inherent variations. In real-world scenarios, perfect conditions are rare, and factors like measurement noise or material inconsistencies can impact our results. So, understanding how precision is affected under these variations is crucial for reliable decision-making. We'll explore methods to quantify this precision and how to account for variability in our calculations. This is especially important because it ties directly into our overall goal of ensuring consistent and trustworthy outcomes in our projects. By mastering these concepts, we can better manage uncertainty and improve the robustness of our systems. Let's dive into how these calculations adapt when conditions are not ideal, helping us maintain confidence in our results despite the inherent variability. Let's take a closer look at this example of pH variation. The nominal pH, which is our target or expected value, is 3. Now, to understand how sensitive our system is to pH changes, we tested it at several different points around this nominal value. Specifically, we looked at pH levels of 2.8, 3, and 3.2. What this tells us is that even small shifts in pH, just a 0.2 unit difference, can be examined to see how they impact our results or system performance. This kind of testing is crucial because it helps us understand the stability and robustness of our process across different pH conditions. So, by comparing these values, we can see how close our actual conditions are to the ideal, and also assess how tolerant our system might be to fluctuations in pH. This is an important aspect of ensuring consistency and reliability in real-world applications, especially when working with processes sensitive to pH variations. Let's take a look at the wavelength variation example. The nominal wavelength we're working with is 254 nanometers. To test the robustness of the method, we checked a few different wavelengths close to this, specifically 252 nm, 254 nm, and 256 nm. Now, if we look at the assay results, they came out very consistently: 99.6%, 99.8%, and 99.7%. This consistency across these slightly different wavelengths indicates that the method performs reliably, even if there's a small shift in the wavelength. The key takeaway here is that the variation in assay results is minimal, which demonstrates that this is a robust method. It's flexible enough to give us reliable results even if the wavelength isn't exactly at the nominal value. This is an important factor when considering the method's overall precision and dependability in real-world testing scenarios. Now, let's talk about system suitability under robustness. When we're evaluating the robustness of our analytical system, there are a few key parameters to consider. First is the %RSD, or relative standard deviation, which helps us assess the precision of our measurements over multiple runs. A low %RSD indicates good consistency. Next, we look at the tailing factor, T, which should be less than or equal to 2. This tells us about the symmetry of our peaks. Ideally, they should be symmetrical, not tailing or fronting excessively. Then, we have the theoretical plates N, which give us an idea of the column's efficiency. The value should meet or exceed the specified limit, ensuring our separation is sharp and well-defined. Lastly, resolution RS should be at least 2. This means our peaks are sufficiently separated, preventing overlap and ensuring accurate identification. To bring this all together, let's consider an example. If we measure these parameters and they meet all these criteria, we can confidently say our system is robust and suitable for reliable analysis. Let's talk about how we interpret the results from our method validation. When small variations occur, they generally don't have a significant impact on the assay, meaning the results remain reliable. These minor changes also don't affect the system's suitability, so we can be confident in its performance. Additionally, such small variations don't alter the resolution between peaks, which is crucial for accurate analysis. This indicates that our method is robust, capable of handling slight fluctuations without compromising quality. However, if we observe a significant change when testing these variations, that tells us the parameter is critical. In such cases, we need to control that parameter very tightly, and this must be clearly specified in our standard operating procedures. Overall, understanding whether a variation is minor or major helps us maintain the integrity and reliability of our method, ensuring consistent and trustworthy results every time. Let's take a closer look at the acceptance criteria we typically use to evaluate our analytical methods. First, we look at the percent assay variation, which should be within plus or minus 2%. This ensures our measurements are consistent and accurate across different runs. Next, we consider the percent RSD, or relative standard deviation, which should be less than or equal to 2%, indicating good precision. Another important point is the resolution, which needs to be at least 2. This tells us that our peaks are well separated, making the results more reliable. We also check for no significant shift in retention time, meaning our method remains stable over time without drifting. Finally, our system suitability tests must pass, according to both our internal standard operating procedures and USB expectations. These criteria collectively help us confirm our method is robust, reliable, and ready for routine use. Remember, these standards are key to ensuring the quality and consistency of our analytical results, which is fundamental to our overall quality assurance process. Let's take a moment to explore the difference between robustness and ruggedness. These terms are often used interchangeably, but they actually highlight different aspects of system resilience. When we talk about robustness, we're referring to a system's ability to perform well under a variety of conditions, including unexpected changes or disturbances. It's about designing systems that can handle variability without breaking down. On the other hand, ruggedness is more about durability and strength, especially in harsh environments. It emphasizes the system's capacity to withstand physical or environmental stressors without failure. Understanding these distinctions helps us make better decisions in designing reliable systems. Robustness focuses on maintaining performance across different scenarios, while ruggedness ensures the system endures tough conditions. Both concepts are crucial to our overall goal of creating resilient, dependable solutions that can thrive in real-world, often unpredictable, settings. Let's talk about the importance of robustness in our methods. First, ensuring reliability is key. We want to be confident that our method consistently produces accurate results. Next, identifying critical parameters helps us focus on the factors that truly impact the method's performance, making our process more efficient. Supporting method transfer is also vital, as a robust method can be seamlessly adopted across different labs or teams without issues. It also plays a crucial role in preventing QC failures, safeguarding product quality, and avoiding costly rework. And finally, robustness is essential for regulatory submissions because authorities look for well-validated, dependable methods. Overall, emphasizing robustness helps us build confidence in our methods and ensures smooth operations from development to regulatory approval. So, in conclusion, robustness measures are all about ensuring that our method remains stable even when small variations occur. This is crucial because in routine analysis, minor changes can happen, and we need to be confident that our results stay consistent. Critical parameters like flow rate, pH, temperature, and wavelength are particularly important to monitor, as they can significantly impact the accuracy and reliability of our method. We evaluate robustness by keeping an eye on several key indicators, such as the assay results, the percentage RSD, resolution, and overall system suitability. By doing this, we make sure that the method performs reliably over time. This approach not only enhances confidence in our analytical results, but is also a mandatory parameter under USP 1225. Ultimately, maintaining robustness helps us deliver dependable, high-quality data during routine analysis, supporting the integrity of our work. For further support, please feel free to contact us. We're here to help you with any questions or additional information you might need. Thank you so much for your time and attention today. We appreciate your interest and engagement throughout this presentation. If you need anything, don't hesitate to reach out. Once again, thank you and have a great day.